Yes, all right, so day 5, we are going to introduce the concept of parametric equations. Okay? Parametric equations. Well, what we're dealing with is we've looked a lot at, how fast something is going or the force or where something is, but we want to incorporate one additional variable, one parameter, and that is the parameter of time. We want to answer the question, not just where did an object go, but when was it at each point? Okay?
I remember this.
When is it at each point? So, here's an example. It says if an object is shot into the air at an angle of 45 degrees at 48 feet per second, you could write the object's height, y, as a function of how far it has traveled horizontally, x. And we would have the equation y equals negative x squared over 72 plus x. We're not going to look at how to develop that formula itself, but here we have the situation where we want to find out when the object will be at a particular position. In order to do that, we need to consider the component form of the original vector to write x and y in terms of time. Now, these are called parametric equations because that time is what's known as a parameter, all right? It's something that impacts the situation, all right? Now look here, we have the rectangular equation is right there, y equals a negative x squared over 72 plus x. We already said that part. But notice here what the original condition was. The original condition of the problem was that something was shot up at an angle of 45 degrees, okay? And it was 48 feet per second. Okay? So it had an angle of 45 degrees, and it was 48 feet per second, FPS. All right? Now, to deal with parametric equations, we want to represent our vertical position at a given time and our horizontal position at a given time. Okay? Now, you see here, we already have the parametric equations written down for us, but I want you to see where these come from. Okay? First of all, horizontally. Horizontally, there's no opposition. We're not going to slow down moving horizontally. It's not like the wind is blowing at us or anything like that. Okay? It's going to be going the same speed the entire time. So for the x, it's just rate times time. Okay? Rate times time equals distance traveled. You all understand that so far?
Yeah.
Okay? Now, the important thing here is to understand what that rate is that we're talking about. Is that rate the 48 feet per second?
It's your magnitude, isn't it?
Well, 48 feet per second is the magnitude.
Yeah, it's your rate. Yeah, that's...
Okay. Why do you say that?
Because you're not going to... Well, you can also increase by an angle, but since you're going to, across an axis, you're not going to increase by an angle, you're going to increase by a certain amount, like a distance.
Okay.
And FPS is the only thing that they give us that considered the distance, unless you can divide that by somehow.
No, that's... What you're saying is true, but again, we're looking to represent x, right?
Mm-hmm.
X, like you said, is going along the axis. Is that initial velocity there going along the axis?
No.
We have to use one of the components. Okay? We have to use one of the components. So as we look at this, what we're going to do is we're going to find the horizontal component, and that's what we're going to use as this rate. Okay? Now, how do we find the horizontal component? Cosine. Cosine. All right? Now, let's look at a triangle kind of outside of the picture just so we can see it a little easier. This rate that we're talking about is this right here. Okay? And we know that the angle was 45 degrees, and we know that this is 48 feet per second. Okay? And that's our right angle. So you're right, we're going to do the cosine of 45 degrees equals the rate over 48. Okay? So our rate is whatever 48 times the cosine of 45 is. What's cosine of 45? Square root of 2 over 2. So it's 48 times the square root of 2 over 2.
That's the square root of 48.
No, it's 24 square root of 2.
Oh, I was. Wait, okay.
Just the 2 cancels with the 48, leaving you 24 times root 2.
Oh, we were multiplying it, okay.
Yeah, we're multiplying.
Okay.
Okay? So, our rate times time here, the rate is 24 root 2, and then we're going to multiply that by the time, t. That's how we get this parametric equation. Okay? So that's the first thing. We've got part of it. Now, did you notice what we ended up doing? We ended up taking the magnitude times cosine. All right. Does that sound familiar? What?
Oh, like for work. A little bit.
We did use this in work a little bit, but the direction, what is our direction angle for the vector? 45. And the magnitude is? 48. How do we get the component form of a vector if we're given magnitude and direction?
It's sine of 45 cosine times magnitude.
That's right, okay? Remember, it's the magnitude, 48, times cosine theta, sine of theta. We figured it out just looking at the right triangle and using right triangle trig, but don't forget about this. This we looked at last time. So, our component vector for our velocity here is 48 times root 2 over 2, which is 24 root 2. And what's sine of 45? Same thing, alright? Good. So it's 24 root 2 for our vertical component as well. Okay?
What's this for? Because we just looked at two different vectors.
Two different components?
Yeah.
What is it?
Well, in this case, they happen to be identical because we have a 45-degree angle. If we shot it at a 50-degree angle, they'd be two different things. Okay? So we have that part. Now let's make a connection back to something we did earlier as well, and that is we're looking for y, which is how high this thing is. You guys remember the height at time t? This formula? Where it's vt minus 16t squared. We did that way back in Unit 3. Okay? They look vaguely familiar. You might also recognize it as vt minus 4.9t squared. That's if we're dealing with meters per second. The 16 is if we're in feet per second. Okay? Well, in this case, this is what we're going to actually use to represent y. Okay? However, what is v when we're looking at this vertical component? 24 root 2, okay? See here the rate, that's our v. So 24 root 2 times t minus 16t squared, that's where we got this vertical parametric equation, okay? Now, this is just one example. But notice what we're able to do at this point. At this point, we could plug in any given time, like time is 3 root 2 over 4, whatever that equals, okay? That'd be like 1.4,
It'd be like close to 1/2, right?
3/4 times 1.4, so it'd actually be a little over 1, okay? But we could plug in 1. Where are we 1 second after this thing is launched in the air? Well, we plug in 1, we plug in 1 for y, and that would give us a position, all right? So one of the things that you have to do, and you can see it here on this graph, is that every time you plot a point, you actually need to give 3 values. You need to show where it is with the x and y coordinates. You also need to label it with time.
Where would you plug in those coordinates? Or
What do you mean?
Like the coordinates, how you find
The t?
like the coordinates is how you find t?
No. In this case, you wouldn't necessarily know the rectangular equation here. You would plug in different times to figure out the x and y.
But what are the
Okay.
coordinates for here?
Well, the coordinates are the x and the y
Oh.
when you plug in those different values. Okay? So that's the concept of a parametric equation. What we're dealing with here, we're concerned with the when. When are we in a specific position? All right. Now, I just want to try one here, okay? We have a set of parametric equations. X equals t squared minus 4, and y equals t divided by 2. So notice here we have a table set up with different values for t. Okay? So if I were trying to find one of the points on our graph, okay, let's start with the -2. If I plug in a -2 squared minus 4, then x equals 0. So I know I'm on the y-axis here. So now I plug in -2 for y equals a -2 over 2, which is a -1. So now I have a point on my graph, 0, -1. So I plot that point, and I also label it t equals -2. Okay? Notice here we're kind of dealing in 3 dimensions. It's just not 3-dimensional space. It's a 2-dimensional plane, but we incorporate the dimension of time here. So we're getting closer to real life. By the time we're done, we'll actually be in real life. We'll have 3-dimensional space with time.
Really?
Okay? The 4 dimensions of real life. Okay? So, take a minute here, try to find the other points and graph what this curve would look like. Alright, so let's look at the points that you guys came up with. When t is -1, what point did we get?
-3, -1/2.
-3, -1/2. Okay, so -3, -1/2 would be right here. And I'm going to label that t equals -1. Okay, this is just how you have to graph with these. Okay? What do you get when you plug in 0?
-4, 0.
Okay? -4, 0. So we are right here. T equals 0. Okay? Jay, what'd you get when you plug in -1, or when you plug in +1?
4.
When you plug in 1, what do you get for x? -3, and what do you get for y? No? Look at your equation, y equals t divided by 2. Just 1 over 2. There's no negative in there. Okay? So negative 3, 1/2 is our point. That's when t equals 1. How about when t equals 2? What point do we have?
Same thing, except a zero,
Zero, one.
What?
I'm trying to make it complicated.
Yeah, I
Zero,
made it
one.
really complicated.
Just say, yeah, 0, 1. Okay. So 0, 1.
5 and 3 over 2.
Alright. 9 minus 4 is 5, and 3 over 2 is 1/2. Okay, so 5, 1/2. Now, this is when t equals 2, this is when t equals 3. Now, this was only defined for negative 2 to 3, okay? So don't have it going off forever in either direction here. But what you should do is you should indicate the direction it's going. Notice what's happening here is this thing moves, okay? It's moving that direction, okay? And you could even put some additional little arrowheads on this if you want to kind of indicate direction. Try that one again. Alright, we're going that way. Now we're turned back and we're kind of headed this way. And we're still headed this way until we reach the point when t equals 3. Okay? So that's how you would graph these. You sketch the points, you show the direction you're moving, you connect them in chronological order. Alright? Connect them in order of time. That's why you need to label the points as you go. Don't label a bunch of points and then go back and try to put your times in. Okay? Because here's the thing, you could have one that has a point here, then a point here, and 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 if you forget what order they go in, you might be stuck, alright? So that's why you label them. Time is 1, 2, 3, 4, 5, 6, 7. I don't even think I did that in the right order. Okay? But then you could show the path.
Is that a graph?
I don't know. It could be. Alright? But that's why we labeled the times. This is where we are. And this is when we are at that point. Okay? Any questions? Make sense? I need some feedback. Does it make sense or no? Do we get it?
Yeah. Go on.
Alright?
Sounds great.
Alright, so, now, graphing in parametric mode. This is something your calculator actually can do. This is kind of cool. Alright? We're just going to do this from t equals negative 2 to 2. Before you get your calculators out though, I want you to do it by hand. Okay? So, let's say half of you do A and half of you can do C.
Back in the B.
I got rid of it. 3 was too many. Alright, so let's do A. Who wants to do A?
Me.
Alright,
Wait, see what
so we got 4.
I see. So
You'll do A. You want to do C? Alright, you could do C. Alright. Carrie, why don't you do C? Jay and Jason and Ma, you guys could do C. 1, how about if you do A, and Bebe and Uran, why don't you guys do C? Okay? So try them by hand first. And do the same thing that we just did. You know, make yourself a little table and plot the points individually, okay? Okay, so that's part A in blue. Part C there in red actually is a parabola. Okay? You'll notice there a couple of the points are the same. So that's how you would graph these by hand, all right? On the calculator, I want to show you with A, and then I'll have you guys try it with C. I want to show you how to do this on the calculator, all right? So let's do this, okay? So the first thing that we're going to do is we're going to go to mode, and you'll notice here, this is probably something you never messed with at all, but it says under mode function, parametric, polar, and sequence. We just did a tiny bit with sequence at the beginning of the year. I think we did one problem where we graphed it. But the parametric, my fingers are too big. Okay. We're going to put it on parametric mode, and now notice this though. When you hit the y equals button, instead of y equals, notice how each separate graph has two equations, x equals and y equals. Alright?
Cool.
Also, notice the little t. It says it's x as a function of t, and y is a function of t. Notice here the button we used to always hit for x, it has x, t, theta, and n. That's because in the different modes, here in parametric mode, it'll give us a t. Alright, so the first one, x was t cubed?
No.
Or
it's just
squared?
T squared.
Okay, x was t squared, so we hit t squared.
Where is the T?
T's right there.
Okay, got
Okay?
it.
And then you go down to y, and that one was t cubed. So
Yeah.
t to the third power. Now, before you hit graph, I also want you to see, if you hit your Windows settings now, notice we have t min and t max. You still have your x window here, but you have t min and t max. We went from -2 to +2. Okay? So now when we hit graph, there's our graph. Okay? Just like what we found.
Mine
Okay.
didn't work.
Yeah, mine's not working.
Now the other thing here is if you hit trace, notice you're given a time, a value of x, and a value of y. And if you plug in a different time, like say 0, notice, remember before if you hit trace you could type in a number and it would go to that value of x. In parametric mode you type a number in and it goes to that value of t. So when t is 0, we are at the point 0, 0. Okay? And I could keep tracing over when t is 1.534, x is 2.354, and y is 3.6118. Okay? So your calculator can do this. Alright? So, why don't you try the other one just to see it work and try something on your own there. Try to graph the other one. Okay. Now, just as an example here, here we have projectile motion. This is one of the things that we often will use parametrics for. Another thing is like things that are moving along a line. Okay? But here we have parametrics, and you'll notice this looks an awful lot like the first example that we did. Okay? The initial velocity is v sub 0. Okay, that's how you would read that. V sub 0 feet per second. Alright? Theta is the angle with the horizontal, so that is the direction angle for our vector. Okay? So notice our parametric equations. X equals v sub 0 cosine theta t. That right there, if you remember, was the horizontal component of your velocity vector when you put it into component form. Alright? And then the vertical component was that v sub 0 sine of theta. Well, notice here, right here, we have this vertical component times t minus 16t squared. Okay? Now, does anyone know what this h stands for? What height? That's good, it is height.
Vertical height.
It's original height. Okay? So this is how we do ones. On the first example we looked at, we were assuming it was shot off of the ground at height 0. Okay? Let's say we were modeling someone jumping off of a diving board that's 15 feet off the water. We'd have a 15 plus
Yeah.
all of that. Okay? Or like in this case, alright, the right field fence in a ballpark is 10 feet high and 314 feet from home plate. So we're talking about baseball. Alright, so we've got our guys standing here. Okay? Here he is. He's got his bat. Alright. He's ready to hit. Okay? And the fence out here is 10 feet tall. And it is 314 feet away from home plate where it's hit. Okay? A baseball is hit at a point 2.5 feet above the ground. Alright, you're not going to hit a baseball off of the ground. That's called golf. Okay? So, we're hitting the ball 2.5 feet off the ground, and then it's going to fly through the air, and it might go over the fence if it's a home run. Okay? But here's the thing. It leaves the bat at an angle of 40 degrees. Okay? So, this initial angle is 40 degrees. Okay? And the with the horizontal at a speed of 105 feet per second. So 105 feet per second. Okay? There's the picture that we're dealing with. Okay? So using these parametric equations, take a moment and try to write a set of parametric equations for the path of the baseball. Alright, so let's check this out, okay? We've got x equal to what in this case? Someone give me your equation.
X equal 105 cosine 40 degrees multiplied with
105 cosine of 40 degrees times time. Okay? So you're doing all of that times time. Okay? And then y would be what?
2.5 plus 105 times sine 40 minus 16t squared.
105 sine 40
T.
t,
My bad.
okay, minus 16t squared. Okay? Now, the cool thing about this is partly why we do this. We can now tell whether or not he hit a home run. Okay? To hit a home run, it has to go 314 feet, right? Horizontally. So, check out what we can do. We can now say, alright, when will it be 314 feet away horizontally? So we would set x equal to 314. And that equals 105 times the cosine of 40 times t. Okay? And you divide by the 105 cosine of 40 and you get t equal to what?
Would it be in seconds or oh yeah, seconds, feet per second.
3 point, what is it?
9.
90,
3.
904.
4. Yeah.
9035 was it?
Yeah.
Okay. Alright, so that is in seconds because our velocity is in feet per seconds. So Here's my question. How do I know if it went over the fence?
You
Plug
have,
this into the second equation.
yeah, but you have to make sure.
There you go.
7.5.
Well, you plug it into the second equation
Say it's bigger than the 10.
and see if it's bigger than 10, okay?
Why 10?
Well, because we already incorporated the 2.5. If we had treated it as though the 2.5 were 0, then yeah, we would say, okay, is it bigger than 7.5? But that's why we put the 2.5 in there. So we plug in that value into your y equation, and y equals
Give me a second.
times 3.9035 minus 16 times
Oh god, that's the one.
3.9035 squared, and you get y equal to
29.4.
What?
You get 29.4?
No, but how did you do that?
you're just plugging it into your calculator at this point.
That's
Okay.
minus 16.
So it's 22.15 feet. So here's the question, did he hit a home run?
Yes.
Does it make it over the fence?
Yes.
Yes, it's higher than 10 feet. It's higher than 10 feet when we are 314 feet away. Okay? So here's the thing, there's two ways that you could do this. We figured out when it would be that far away, all right? And then we saw, will it be high enough when it's that far away? And the answer was yes. We could have also set this y equation equal to 10. And we could have then figured out two different values of t. The first one would be on the way up, so we'd ignore that one. The second one would be when the ball's on the way down. Okay? Now this is more complex because you have to solve a quadratic equation. Alright? Also, then you would plug it into x and you would see, okay, by the time it gets back down to 10 feet, have we passed 314 feet? Okay? So it is a more complex way of doing it, alright, than the way we did. Okay? Questions? I know you may not be as familiar with baseball, that's okay. I try to avoid scenarios where you may not be as familiar with them when it comes to a test or something. But there we go. Okay? Now, before I turn the page, don't look. How do you think we do parametrics in 3 dimensions?
I don't want to do that.
Oh, you just add one more variable.
You just add one more equation. So instead of x equals and y equals, now we have
X,
X,
Z.
Y.
z equals as well. Okay? That's all there is to it. Like most of the other things that we've dealt with, it's just x equals, y equals, z equals. Now we have this third thing. And you'll notice what we have here is you're going to be given a parametric equation, or you're going to be given a velocity vector. Okay? That vector is in 3D. You're not going to be given the ones where you have an angle, because remember, we don't really deal with direction angles in 3D at our level. Okay? So, we have this direction vector, v, and it goes through a specific point. Now, the point is x sub 0, y sub 0, z sub 0. Okay? When you use that point, you're going to assume that t is 0 when you're on that point. Okay? So, we're starting at the point x sub 0, y sub 0, z sub 0, and that's when t equals 0. Alright? That's why we use that notation. But you take the x component of your velocity, and that's what you multiply by t. You take the y component of your velocity, and that's what you multiply by t. You take the z component of your velocity, and that's what you multiply by t. Alright? So, nothing to it. Let's look at one. Okay? We're going to find the parametric equations of the line L. And line L passes through the point 1, negative 2, 4, and it's parallel to v equals 2, 4, negative 4. So it gave us a direction vector, and it gave us a starting point. Okay? So our line L is going to have an x parametric equation, a y parametric equation, and a z parametric equation.
But use this formula is like y plus something x plus something. Why is that so?
I can't hear what you're saying. Why am I doing what?
Yeah, like y plus x plus at and y plus dt, and it's still equal x or still equal y.
Well, because that x, y, and z in the equation there is the x when t is 0. Alright? So notice here, I have x. When we say it goes through the point, we're going to assume that that's when t equals 0. Okay? We're going to let t equal 0 there. So notice what I do when I'm writing my parametric equations. Watch this. I'm going to put down the coordinates of that starting point as the first part of my 3 equations. And then my velocity is 2, 4, and negative 4. So I'm going to put a plus 2t, a plus 4t, and a minus 4t. And now I have my 3 parametric equations. That's it.
What the?
That's all you got to do. That gives us the equations that represent line L in this case. Okay?
That was way too
Okay?
Okay. Oh, the next slide is gonna be like JPEG.
So that's really it, guys, okay? At this point, what I'm going to have you guys do is we'll start doing a little bit of practice, okay? You've got some IP for this section, but it's on writing parametric equations, both in 2 dimensions and 3 dimensions, okay? The models that we're using, a lot of those will give you the equation, or at least a structure for the equation, but you're going to be graphing some in parametrics and just working with these parametric equations, all right? Again, this is essential that you get down this lesson, all right? So even if you aren't in the habit of doing all your IP, make sure you do all your IP for this section, okay? All right.